The last topic for this chapter is polarity. And polarity will feel very nitpicky when we first start looking at it. All it is trying to figure out which direction the electrons are sitting on. However, polarity is the reason that salts dissolve in water. Polarity is the reason that oil does not dissolve in water. Polarity is the reason that oxygen is a gas because it doesn't have polarity, but ammonia is a gas at room temperature, but water is not a gas at room temperature. So polarity has this like cumulative effect. When you think of how many millions and millions and millions of atoms we're talking about, it has a cumulative effect. And so why does it matter what is polarity? So this is not a perfect picture by any means, but if you imagine that you had a bag full of magnets and they were positives and negatives, and you kind of put them near each other, spread out across the floor, I'm sure that what you could find is that the ones is that like as long as they were close enough to each other, you would end up with a nice situation where they all were like positive, negative, positive, negative. As long as you kept it, single file. And you know that the positives aren't going to want to be near the negatives. So in a way, what that's saying is that has structure for the magnets. If you did the same thing with, let's say, dominoes of the same size, notice they don't have a charge side, so they're just sitting there, right? So if you put them near each other, they might end up like this, they might end up like this, they might end up like that. They're going to end up all crazy like. Even if you put them near each other, they're not going to have any preference for how they line up. This matters. If this happens, what it does is it lowers the boiling point, which means that something that you would expect to be a gas is actually like a liquid or a solid. It lowers the boiling point. It affects viscosity. It affects melting point. It affects, solubility. It affects all those things. Over here, when everything's all kind of scattered like that, then those things aren't in play. Like they're not affected because you don't have any positive or negatives. So electronegativity is saying that if something has enough electronegativity, it will cause the atoms or the molecules to do this. So electronegativity is where the electrons are kind of like sitting on one atom in the bond and they're not very much on the other atom. And so it kind of sort of makes it it's not a real magnet, but I'm using the word magnet as the example. It kind of makes it so that one side is like a positive-ish side and one side is a negative-ish side. And then they line up and they have structure. So electronegativity, again, that's how strong atoms attract bonding electrons. So we have this table. It was created by this guy named Pauling, and he decided that the maximum of the table should be 4. And then it goes to 0. So 4 is the maximum. I don't know. It's just funny. Like, I'm going to make the maximum value of 4. Okay. So that's 4. So if you look and you compare, let's say that we have a bond between oxygen and fluorine, the difference in their electronegativity values, it tells you something. First of all, if you have a difference of greater than 0.4, it tells you that it's a covalent bond. Secondly, it tells you since the 4 is bigger than the 3.5, it tells you that both of the electrons are sitting over there and there's a whole lot of place where the oxygen, he wants his electrons, but he's not strong enough to entice them back to himself. So it's like the fluorine right here is holding out like massive amounts of ice cream sundaes to these electrons and they are like, we are so at dessert time. And the oxygen's like, but I've got a salad. And they're like, yeah, no, we're going to have the ice cream sundaes. So it's like that is happening the whole time on the molecule. And so because electrons are negative, it kind of sort of barely makes it so that there's kind of like a directionality to the magnet, like I was kind of showing you. Like there's a positive-ish side. So this is kind of the positive side, and that's kind of the negative side. We could draw it with an arrow, or we also would draw it. These are deltas. So a positive delta and like a negative delta. So those are 2 ways to draw it. You can do the arrow or the delta. So let's look and let's go back to the idea of electronegativity and see what's going on. So we have some compounds over here. And if you look, you'll notice that these values are the values on this chart. Note, this chart changes. It gets updated constantly from people releasing research papers. This is an electronegativity chart is not the one all be all electronegativity chart. If you Google online, you will find other electronegativity numbers. Like maybe you'd find oxygen is 3.446. You might find oxygen is 3.5001. So it's still in the right range, but I'm just saying the numbers are going to be slightly off. So that's okay. The idea is, like, generally speaking, once you get the idea behind electronegativity differences, we'll just kind of use the trend of electronegativity, which says that this side here is the high end of being electronegative. So look at these atoms and make sure you can see where the 0.9, the 3, the 2.1, the 3. Look on the chart, make sure you find them. Make sure you're okay with those being the values for each of these. And then make sure you're okay with what they equal. So you can go ahead and pause the video to double check all of that. So now that you've done that, use these three terms. You have ionic, you have two kinds of covalence. There's this word polar and then there's pure. Also turn this into a greater than sign with a or equal to. So take these numbers and classify them as what they are. Go ahead and pause the video. Okay, so you should have gotten that this was ionic. You should have gotten, I'm going to put a P in front, a polar. I'm going to put polar C. Again, this is polar C. This is pure C. And this is pure C. So look, did you already know that sodium and chlorine formed an ionic bond? Probably, because we've talked about that. If you're on the left and the right side of the stair-step line, you got an ionic bond going on. So, same thing here, polar covalent, though. Not same thing, but that's polar covalent. So, polar covalent, what that means, and we already talked about how hydrogen with some things, his spacing, he's a 2.1, so he kind of sort of falls right here. That's hydrogen's. Again, he's just off because it's hydrogen. So the 2.1, between the 2.1 and the 4, right here, this 0.7, we call that being pure covalent. So it's like saying we have this and we have this. We're on the same side of a chart, so we're saying that that's covalent. We're also saying those are different atoms. And look at how different their electronegativity values are, 2 and 3.0. So there's some directionality to the electrons and where they want to sit on that bond. Same for a C and a Cl. So C is 2.5 and Cl is 3.0. So again, some directionality. Now, right here, there gets a point where the atom doesn't recognize. So this is pure because there is no difference. So there's no way that one can pull over the other. But in the case of HCH, that is still considered a pure covalent bond. And it's just the difference isn't enough. Maybe they are pulled just barely-ish over, just a little bit, but it's not enough for the molecule to recognize or to line up or to do anything about it. So this is also considered a pure covalent bond. So if something is covalent, it's on the side of the chart. We've already talked about that. But if they start separating pretty far apart, then it's kind of like they have a little bit of maybe an ionic nature to them, this positive negative lining up. We're not saying that they're ionic, but we're just saying maybe they have a little bit of that nature. So let's look at the bond dipole, and then we're going to end up looking at our chart and make sure that everything is good. So we have a bond dipole. Notice that I've got two ways that this is written. It's written either with deltas or it's written with a line. Notice that the hydrogen is supposed to fall here, but chlorine, it's way over here. So he's further over. This is 1, 2, 3, 4 steps, whereas the chlorine's just 1 step away. So the chlorine is definitely the more electronegative. So it means in this bond, the electrons are sitting over here by the chlorine who's offering out ice cream sundaes. They're sitting over there. So it makes this whole side negative-ish and this whole side positive-ish. So if you have another one that comes and lines up, it's going to line up in a certain specific way. And that's the point of why we are talking about this. Oops. It's going to line up like that. It's not going to line up here or here because, look, the positives are going to be near each other and the negatives. It's going to line up there or there, where the positive and the negative sides are near each other. Let it stay. Nope. Okay. So we call that having a bond dipole. When that happens, it has a bond dipole. And as the electrons are pulled towards the more electronegative, one atom is left with a partial positive, and a partial negative. Notice dipole, bond dipole, two poles like a magnet, you know? And then that's one feature of it. So if we look at a bond, we can look and we can see what they are doing. So if you look at this electronegativity difference, each of these bonds have this directionality to them, with these oxygens being more electronegative. And same here, the hydrogen is 2.1 and then the 2. So they've got this electronegativity difference also. So once you look at the bonds, you're like, oh, yeah, there's the dipole. You have to then look at an overall picture. And this is what throws students sometimes. If your bond dipole ends up directly opposite each other, so see how these are opposites, completely opposites? If they end up opposite, then what that means is that they will cancel each other out. And overall, the molecule, it's not negative or positive on either side. It's kind of like saying that, yeah, these electrons are heading over here, and these electrons are like more over here, but then the carbon atom here, like this one is having maybe a little bit of an influence on those, and then maybe this one is having like a little bit of influence on that. You can think of it that way at least. But directionally, if they are directly opposite each other, there's no positive or negative. So this one does have bonds, but overall it has none. But then compare it to this one. Notice that these ones, they aren't directly opposite each other. They're kind of going in the same direction. Do you see that? So overall, the whole thing has a bond dipole. And that means that when another one comes nearby, it's going to land right there, because that's the negative. The oxygen is kind of the negative side, and below the oxygen is the positive, or maybe right there. It's not going to run to go side by side with any of those hydrogens. So you have to be able to recognize when you look at molecules whether or not they're going to have a bond dipole, and then whether or not they have an overall dipole. I do have a rule of thumb that will help, especially if you have a really hard time seeing things three-dimensionally. You will get better at it, especially in organic chemistry. So most things will be polar. All right, so just go with that to begin with. Most things will be polar. So if you have to guess, I'd guess polar. But if all the external atoms are the same, they might be nonpolar in these cases. If there are no lone pairs and all of the atoms are the same, then it's going to be nonpolar. If there are lone pairs with the same external atoms, and it's either square planar or linear, those also are going to be nonpolar. So this might be like an overall rule of thumb to come back and glance at, but we're going to look at the chart and we're going to make sure that you can see these pictures.